welcome back. So, let us finish the discussion on the internal combustion system, where we are doing the SI and CI engine discussion. So, what we stopped in the looking at this two stroke engine. This is the two stroke engine operating cycle. So, this is a two stroke SI engine operating cycle. So, there are essentially primarily two stroke. One is there are the different components. This is a schematic. Every engine has its design, but essentially it operates on two stroke, and one is the compression stroke and other one is the expansion of the power stroke. So, what it does that it actually in the compression strokes actually starts by closing the intake, inlet and the exhaust port, and then compress the cylinder contents and draws fresh charge into crankcase, and this happens once the piston approaches towards the top center, and at the same time the spark plug ignites it and the combustion is initiated. Now, in the second stroke, whatever is your power and expansion stroke, it is similar to that your 4 stroke cycle, and that happens until your piston approaches to BC. When the first and exhaust port and then the intake ports are uncovered. Now, here all the burn gases, or rather most of the burn gases exit cylinder and in an exit blowdown process. So, this is what happens, and when the inlet ports are uncovered, fresh charge which has been compressed in crankcase flows into the cylinder. So, that is how this process actually continues. Now, this schematic is your 4 stroke CI engine or diesel engine cycle. First one is your intake, second one is your compression, third one is your power, and this is exhaust. So, these are the again the 4 stroke like your SI engine. So, this is the operating cycle, this is the piston head connected with the crankshaft, and here this is your essentially fuel injector, intake valve, exhaust valve, and all these are there. So, operating principle is pretty much similar to your 4 stroke SI engine, but here your fuel is injected from here and fresh air comes in. So, cylinder only contains air. So, this is what air comes in. Okay. So, intake air comes in, then compression takes place, where actually the reaction is initiated, and then finally expansion, and this goes off. So, this is how the different cycle things works. Now, if you look at this combustion in SI engine, there would be one is the mixture preparation. This is require carburation, which is no longer used in pretty much in the North American market. Then your port injection, where fuel is sprayed into the air stream just before the inlet valve. Then there could be have a direct injection, fuel is injected into the cylinder. So, this is your DISI, direct injection system. Then you have ignition, which is through spark plug, and then the flame, which is the flame kernel will develop and there will be flame propagation. Then you will have some parameter for quantification. One is engine knock. So, that is because of your fuel octane number, engine compression ratio, then you have pollutant formation. One is the NOx, CO, UHC. So, these are the, now finally your exhaust treatment, which is your catalytic converter and all these things. Now, there are also now the recent development, that is the hybrid vehicle. So, that means now that has opened up another area of research where these hybrid vehicles are gaining more popularity, and then you can avoid lot of these issues of your pollution and all these things, and also then you may not need to use either gasoline or diesel, that kind of fuel, or hydrocarbon fuel. So, in a hybrid it would be more powered by the battery, and that is where your fuel cell technology, these things, they are becoming quite popular. But obviously one issue is that the sustainable of that fuel cell, how long it can sustain, how much power production it can give you, all these things are there. So, this is, we have already seen that this is an simple cross section of SI engine, SI engine combustion chamber. So, that is an simple cross section of that. Now, if you see the diesel engine operation, now this is how the diesel engine operation takes place. Now, there are in your CI engine, compression ignition engine, the operation takes place in this many processes are there. So, there could be, when you look at the CI operation, so there is a direct in cylinder injection DC for large engine. So, there could be pre-chamber injection also. Then you have spray, which is compression ignition or ignition delay. So, issue is that ignition delay, compression ignition, all these are there. Then fuel cetane number, obviously pollutant formation are there, pollutants they are there, NOx, CO, HCO, your catalytic converter, all these are your important component of that. These are your CI engine components. And operation wise, if you look at it here, you have air inlet, inlet port design, chamber design, turbocharge, these are the, so that will dictate your air motion or the turbulence in the combustion chamber. Now, on the other side you have the spray characteristics and all these things. So, that will basically the fuel properties, which will direct impact of ignition, fuel air mixing process. Now, this when you have an injection, the injection timing is one important thing, then injector system design is another important thing, injection duration is another, injection rate. So, these will actually determine these spray characteristics and all these things, because this will tell you that what kind of spray you are going to have it, and that has the impact or the direct impact on the combustion characteristics inside the cylinder. When that happens, basically that goes to the mixing process. Obviously, mixing is indirectly also impacted by the some of the fuel properties. So, this is a mostly non-premix combustion or partially premix combustion. So, once the combustion takes place, you have heat release which is obvious, then the radiation effect on the wall, polluted formation, soot and all these things. Then either you can send it to exhaust or you recycle through easier and send something back to the chamber and again. So, easier is another advantageous technology which allows you to improve the thermal efficiency of the system. It inducts back some of these exhaust gases to the fresh mixture. So, the heating of the fresh mixture or their temperature. So, easier allows you to control the temperature of the incoming mixture there or the reaction temperature also to remain under some control where your pollutant formations are not that high. So, these are now lastly we can look at this, it is an HCCI system where your diesel engine is a compression ignition engine, this is fuel injector, this is the system, or gasoline engine is a spark ignited where premix mixture gas are sitting there. These are the two which we have already discussed, because this is CI, this is SI and this is HCCI. This is homogeneous charge compression ignition. That means this allows you to have ultra low emission. So, that is one of the technology where the industry people are really looking forward, and if this comes in place, that would be a huge advantage from pollutant formation side. But as I mentioned already, there is already a huge thrust in the western country to come up with the hybrid vehicle, so that you can avoid these things, the pollutants and all these things, as long as you do not burn the hydrocarbon fuel. But again, that hybrid vehicle is supposed to be more sustainable and these things. Now, that is pretty much what we want to discuss about the combustion system. Now, another area that comes under the basics that we will discuss before we move to the turbulence. So, that is Rankine Huguenot relation. So, that is what we do. Now, this is for steady 1D flow of combustible or combustible gas which that burns to completion. So, we look at the equations relating to initial and final condition, and we can derive them from the conservation equation. Now, let us consider a premixed flammable mixture, premixed flammable mixture. So, you have a long tube, inside that you have a mixture which is coming premixed mixture from one end. Okay. Now, obviously, if you have that, the combustion will travel down to the other end if this is the ignition point. If this is the ignition point, from the ignition point the wave will travel to the other side. Now, if both the ends are open to atmosphere, then the velocity of this combustion wave would be order of 1 meter per second. But for most hydrocarbon air stoichiometric mixture, this typically for hydrocarbon CNHY, this is order of 0.4 to 0.6 meter per second. So, how is it controlled? Essentially, the velocity of this wave is primarily controlled by the diffusion of heat and active radicals. So, this is what normally called as flame. Now, once we are talking about the flow property, we call it a deflagration. Now, other case, if the tube is closed from the one end and then it is ignited at the other end, then the propagating wave will go, it will go from transition from subsonic to supersonic speed under the right conditions. And if that happens, that supersonic wave, this is called detonation. Now, in the detonation, heat and radial diffusion or radical diffusion do not control the velocity. Rather, so in detonation, so it is more controlled by the shock wave structure of the supersonic wave. So, that will control the temperature, pressure and all these things. Though it is I mean the detonation wave is always 3-dimensional, but we can do a simplified analysis, simplified 1D analysis of the same. So, we can do that. So, that is what we wanted to do it. Now, let us put an tube like this, and in between there is these things. This is let us say V1, this is V2, this is product, that means hot gas, P2, T2, rho 2, Mach 2, and this is reactant. This is also cold gas. So, let us say it is P1, T1, rho 1, Mach 1. Some assumptions which are there associated with this one dimensional analysis is that 1D steady, that is number 1. A of the tube constant, that is number 2. Number 3, ideal gas constant and equal specific heat. Then adiabatic conditions, that means there is no heat loss through the wall of the tube, and obviously any external other forces like body forces, these are neglected. So, these are the assumption behind this one dimensional analysis. So, first thing that one would like the mass conservation. So, the mass conservation, you get m dot equals to rho 1 V 1 equals to rho 2 V 2. Now, second is the momentum conservation. Only force acting on the control volume is the pressure. So, we will take P 1 plus rho 1 V 1 square equals to P 2 plus rho 2 V 2 square, which is second, and I can write energy conservation equation, which is H 1 plus V 1 square by 2 equals to H 2 plus V 2 square by 2. So, this is again pertaining to these conditions. This is my control volume, and 1 stands for the reactant side. Now, if you split the total enthalpy into two components, one is the sensible enthalpy, another is the heat of formation, we get summation of yi and then summation of yi T naught to T Cpi dt. So, that is what. Now, since we have made an assumption like its constant and equal specific heats. So, this equation can be written as summation of yi hi plus Cp T minus T naught. So, this is what I will get my enthalpy. Now, I will put this 5 into 3 or in the energy equation. So, once I do that, what I will get? I will get Cp T1 plus V1 square by 2 plus summation of yi HFI naught minus yi HFI naught equals to Cp T2 V2 square. So, this is, you can think about state 1, this is state 2, and this is in total you think about heat addition, which is Q. That is my equation number 6. Now, if you simplify this, then the energy equation gets simplified too. So, after simplification, what we get? Cpt1 plus by 2 plus Q equals to T2 plus by 2. That is what we get. Now, we have made one more assumption, is the ideal gas assumption. So, once we have or incorporate that ideal gas assumption, so using ideal gas assumption, what we get, that P1 equals to rho 1 R T1, P2 equals to rho 2 R T2. So, this is what we can write. Then we combined, now combining equation 1 and 2, we get P2 minus P1 divided by 1 by rho 2 minus 1 by rho 1 equals to minus m dot square. This is my equation number 9, and that actually gives you an equation for Rayleigh line. So, this is an equation for Rayleigh line. Now, we can actually plot, P versus 1 by rho for fixed mass flow rate. So, this will give you the Rayleigh line. Let us say for fixed P1 and rho 1, we get P equals to A into 1 by rho 2 plus B. This is for fixed P1 and rho 1, where slope A equals to minus m dot square and intercept B equals to P1 plus m dot square into 1 by rho 1. So, this is what we get. If you plot this, this is the axis, this is 1 by rho, this goes to P1 plus m dot square. So, essentially this is for P axis. Now, we can get a curve like this, and this is 1 by rho 1, this is zone A, this is B, and this would be P1, and this slope is, intercept is P1 plus m dot square into 1 by rho 1. So, that is my intercept. So, now what you can have different mass flow rate, and you can see the lines would be like this. So, this is the increasing m dot. So, with the increasing m dot you get different Rayleigh line. Now, these are division. So, here your for state 1, this Rayleigh line for state 1 is P1 and 1 by rho 1, which is fixed. So, once we increase the mass flow rate, the lines become much more stiffer. Then one can see that the limit of infinite mass flux, then the Rayleigh line would be vertical like this. This is infinite mass flux, while at the opposite limit of 0 flux it is horizontal. So, this is what you get. Now, there are two quadrants which are level A and B. So, these are essentially A and B, these quadrants are physically inaccessible. So, this figure will later used to decide what final states are possible for detonation waves. So, that we will do, or rather use this one for the later stage to decide that thing. Now, Rankine-Huguenot, this is a Rayleigh line plot. Now, the Rankine-Huguenot curve we can obtain from the energy equation. So, this we can obtain from the energy equation along with the energy equation along with mass and momentum conservation. So, which we have here at 1, 2 mass and momentum conservation and the energy equation at 7. So, that is essentially equation 1, 2 and 7, and where you can also ideal gas relation will gamma equals to Cp by Cv. So, if you do that and combining this all this, we can get the expression like gamma minus 1. So, using mass, momentum and energy, gamma by 1, P2 by rho 2 minus P1 by rho 1 minus half P2 by P1, 1 by rho 1 plus 1 by rho 2 minus Q equals to 0. So, that is, so here we further assume that Q is a known parameter, and then we will fix the value of P1 and 1 by rho 1 and look at the other parameters, and so we will stop here and take it up from here in the subsequent lecture. Thank you.